Last time we saw how to evaluate the integral 1 over 12 cosine 2x plus 5 sine 2x plus 13 dx using the substitution u equals tangent x. However, at the end of that video, I said because of this very special nature of the numbers selected for the denominator, 12, 5 and 13, you can also evaluate this integral without using the substitution u equals tangent x. Well, in this video today, I'm going to explain you how to evaluate this integral without using the substitution u equals tangent x. Last time, the answer that we obtained was negative 1 over tangent x plus 5 plus c. Today also, we will see if we can obtain that very same answer, but this time without using the trig substitution u equals tangent x. However, please note that this is a special question with these numbers 12, 5 and 13. What is so special about these numbers? They are from a Pythagorean triple. We know 12 squared plus 5 squared is going to be equal to 13 squared. In such cases, the method you are going to see in this video works flawlessly. Alright, to answer this question without using the trig substitutions, first of all, identify the numbers as from a Pythagorean triple. Since these numbers 12, 5 and 13 are from a Pythagorean triple, I'm going to divide both numerator and denominator by 13. Remember, 12 squared plus 5 squared is equal to 13 squared. I'm going to divide both the numerator and the denominator by 13. Let me write down this integration one more time. I have 1 over 12 cosine 2x plus 5 sine 2x, and we also have a 13 on the numerator. I have dx. I'm going to write down all the terms in the denominator within parentheses. Then what I'm going to do is I'm going to divide both top and bottom by 13. Next, this 1 over 13 from the numerator will be written outside of the integral. Let me go to the next line. I have 1 over 13 integration. On the numerator, I have a 1 divided by, for the denominator, what I'm going to do is each individual numerical value, 12, 5 and 13, will be divided by this 13. When I write them down, I have 12 over 13 times cosine 2x plus 5 over 13 times sine 2x plus 13 over 13, which is equal to 1. And in addition to that, I have a dx on the numerator. Alright, now I'm going to do a special construction. In fact, I'm going to draw a right triangle. The right triangle has one side whose length is equal to 12 and the other side whose length is equal to 5. In that case, we know that the hypotenuse should be equal to 13. Alright, let me assume that this side is equal to 12, maybe 12 inches. Let me assume that this side is equal to 5, maybe 5 inches. In that case, I know that the hypotenuse should be equal to the square root of 5 squared plus 12 squared, which is equal to 13. Alright, what I'm going to do next is I'm going to label this angle right here as angle 2 alpha. As soon as I do that, I can identify cosine 2 alpha is equal to the adjacent divided by hypotenuse, which is 12 over 13. And then I can identify sine 2 alpha. Sine 2 alpha is opposite over hypotenuse, which is 5 over 13. Similarly, if necessary, we can also write down tangent 2 alpha, which is equal to opposite over adjacent, which is 5 over 12. Even though right now I don't need tangent 2 alpha, later I will need that. Next, what I'm going to do is I'm going to look at the denominator of the integral. The first term is a 12 over 13 term. That 12 over 13 will be replaced by cosine 2 alpha. Right here I have a 5 over 13 term. That term will be replaced by sine 2 alpha. And I will not forget to write down this plus 1 also when I write down the terms of the denominator. Alright, now this integral has become equal to a 13th integration. On the numerator, I have a 1 divided by 12 over 13 is going to be written as cosine 2 alpha, that times cosine 2x, plus 5 over 13 is going to be written as sine 2 alpha, that times sine 2x. And don't forget, we have a plus 1. On the numerator, we also have a dx term. Alright, now look at the denominator of the integration once again. I will only look at this part of the denominator for now. I will also pay attention to plus 1 later, but at this point, I'm going to only look at the highlighted segment of the denominator. In the highlighted segment, I can see cosine 2 alpha times cosine 2x plus sine 2 alpha times sine 2x. In fact, it was an intentional arrangement. If I go back to this triangle, in case if I had labeled the angle right here as angle 2 alpha, then I will not have cosine 2 alpha being equal to 12 over 13. I was careful to pick the angle right here as 2 alpha so that 12 over 13 is cosine 2 alpha and 5 over 13 is sine 2 alpha. Then only this part of the denominator became cosine 2 alpha times cosine 2x plus sine 2 alpha times sine 2x. So when you select those lengths of the triangle, you have to be careful on that. Alright, now what's the purpose of writing it as that? Because if you pay attention on cosine a minus b expansion from basic trig, you know that this is equal to cosine a times cosine b plus sine a times sine b. Well, I can use that identity with, let's say, a equals 2x and b equals 2 alpha in order to replace this highlighted segment of the denominator. Let me go ahead and use that identity with a equals 2x and b equals 2 alpha. Now this integral is equal to a 13th integration 1 over cosine a minus b, which means cosine a is equal to 2x minus b is equal to 2 alpha. I should not forget that there is a plus 1 also still remaining in the denominator. Let me go ahead and write that as well, plus 1. And then we have dx on the numerator. Alright, now when you look at this first part of the denominator, I can actually factor out a 2 from inside the parenthesis. Then I can write down this first term as cosine, I will open bracket, 2 open parenthesis x minus alpha, close parenthesis, close bracket. In addition to that, I have this plus 1 in the denominator. Now, when you look at this term, what trig identity comes to your head? Well, we know that cosine 2 theta has 3 expansions, but I'm going to use the expansion that cosine 2 theta equals 2 cosine squared theta minus 1. I can rearrange the terms of that identity as cosine 2 theta plus 1 being equal to 2 cosine squared theta. Well, the denominator right here is exactly similar to the left hand side of the identity right here, with 2 theta being equal to 2 times x minus alpha, which means our theta should be equal to x minus alpha. Well, I'm going to replace all of this highlighted denominator by the right hand side of this identity with theta being equal to x minus alpha. Then the integral now becomes a 13th integration 1 over 2 cosine squared theta. 2 cosine squared theta is equal to x minus alpha. And then we have dx. Alright, what I'm going to do next is I'm going to write down this 2 outside by combining with the 13 on the denominator outside of the integral. Then the integral becomes 1/26th integration 1 over cosine squared x minus alpha dx. We know 1 over cosine theta is equal to secant theta. Therefore, 1 over cosine squared x minus alpha should be equal to secant squared x minus alpha, and then we have dx. Alright, now we are almost done, because from the standard table of integrals we know that integration secant squared theta d theta is equal to tangent theta. Since this alpha is a constant, I can apply this identity directly to solve this integration. Therefore, this integration becomes 1 over 26 tangent x minus alpha. In fact, this integration is an indefinite integral. Therefore, I will also need a plus c, where c is an arbitrary constant. Alright, now this is a final answer. This is a final answer because alpha is a well-defined angle. However, if you would like to proceed, and if you would like to keep the answer only in terms of x, we may do so. In order to do that, we have to apply the tangent a minus b expansion for this part, and then we have to simplify it along with the 1 over 26. So let's first find tangent x minus alpha term. We know tangent x minus alpha should be equal to, using tangent a minus b identity of trig, this should be equal to tangent x minus tangent alpha, all that's divided by 1 plus tangent x times tangent alpha. Alright, now all we have to do is to replace the value of tangent alpha in these two places of this identity in order to find tangent x minus alpha. Then we can go ahead and replace tangent x minus alpha in this final answer. However, do we know tangent alpha? Well, let's go back to the triangle that we drew earlier. Here's the triangle that we drew earlier. We have tangent 2 alpha. We do not have tangent alpha, but we have tangent 2 alpha being equal to 5 over 12. In fact, we can use that information and hence obtain tangent alpha. However, please remember something very important. According to the geometry of this triangle, 2 alpha is an acute angle. Or in other words, 2 alpha is an angle between 0 and 90 degrees. If 2 alpha is an acute angle, alpha should also be an acute angle. In fact, since 2 alpha is between 0 and 90 degrees, alpha should be between 0 and 45 degrees. Which means tangent alpha should be positive. Please remember that statement. Tangent alpha should be positive. Alright, now we are going to use this information, tangent 2 alpha being equal to 5 over 12, and hence obtain the value of tangent alpha. We have tangent 2 alpha is equal to 5 over 12. Now we can use the expansion of tangent 2a from basic trig. We know from basic trig that tangent 2a is equal to 2 tangent a divided by 1 minus tangent squared a. By applying that identity here with a equals alpha, we have on the numerator 2 tangent alpha divided by, in the denominator, 1 minus tangent squared alpha. All that should be equal to 5 over 12. Now we can simplify this one, and then we have 12 times 2 tangent alpha becomes 24 tangent alpha. That should be equal to 5 times 1 minus tangent squared alpha. Now this can be rearranged to look like a formal quadratic equation. This equation becomes 5 tangent squared alpha plus 24 tangent alpha minus 5 being equal to 0. Alright, that equation has nice factors. If you factor this equation, we have 5 tangent alpha minus 1 times tangent alpha plus 5. This is equal to 0. Now we set each factor equal to 0. Then we have 5 tangent alpha minus 1 being equal to 0, and also we have tangent alpha plus 5 being equal to 0. Now from this first equation we get tangent alpha is equal to 1 over 5. From the second equation we get tangent alpha is equal to negative 5. Earlier we said tangent alpha cannot be negative because we said alpha is an angle between 0 and 45 degrees. Therefore, we rule out the possibility of tangent alpha being equal to negative 5. We conclude that tangent alpha should be equal to 1/5. Now we can go ahead and use this value in order to find tangent x minus alpha. We have tangent x minus alpha being equal to tangent x minus tangent alpha, which I will write as 1/5 divided by 1 plus tangent x times tangent alpha, which is 1/5. In order to simplify this, what I'm going to do is I'm going to multiply both top and bottom by 5. When I do that, I get tangent x minus alpha being equal to 5 tangent x minus 1 divided by 5 plus tangent x. Remember, that's the answer for tangent x minus alpha, which is not the answer for our question. We were working on integration 1 over 12 cosine 2x plus 5 sine 2x plus 13 dx. We showed that the answer of this one is equal to, let me go back and check that answer, all of this. 1 over 26 times tangent x minus alpha plus c. All of that's equal to 1 over 26 times tangent x minus alpha plus c. What I'm going to do next is I'm going to replace tangent x minus alpha by the value that we evaluated here. Then this becomes 1 over 26. Let me open brackets. Tangent x minus alpha is equal to 5 tangent x minus 1 divided by 5 plus tangent x plus c. Alright, now we can keep this answer as a final answer. However, you may be wondering whether this is equal to the answer that we obtained for this very same integral using the trig substitution u equals tangent x. In fact, this answer, if simplified some more, becomes the answer that we obtained using the substitution u equals tangent x. The answer we obtained using u equals tangent x was negative 1 over tangent x plus 5 plus c. Well, for those who have not yet seen that integration using the trig substitution u equals tangent x, I will have the link posted down below in the description. You can see that the answer obtained in that video is equal to negative 1 over tangent x plus 5 plus arbitrary constant c. Just to avoid any possible confusions, I will show you that even this answer can be simplified and reduced to be equal to that very same answer. In order to do that, what I have to do is I'm going to rewrite this integral as 1 over 26 bracket. I will write down the denominator first. In the denominator, I have 5 plus tangent x. In the numerator, I have a 5 tangent x minus 1. Instead of writing it as that, what I'm going to do is I will write it like this: 5 times 5 plus tangent x. Well, that is not the required numerator. If I multiply 5 times tangent x, of course I get 5 tangent x. We need 5 tangent x on the numerator. However, the constant term I get is 25 instead of the negative 1 right here. In order to create a negative 1, all I have to do is to subtract 26. Now I have this negative 1 also on the numerator. Let me close the brackets, and then there's this c. Alright, what I'm going to do next is I'm going to split this fraction right here into 2 pieces by grouping this part as one fraction and by grouping negative 26 over 5 tangent x as another fraction. When I do that, I get 1 over 26. Let me open bracket. When I group this part, I can see 5 plus tangent x terms will be cancelled from the numerator and the denominator. Then I'm just left with a 5. And then I have this minus symbol. When I group these two pieces, there's nothing to be cancelled. I need to write them down as they are. I have negative 26 over 5 plus tangent x, and there's this plus c. Now I can do some further simplifications. I'm going to distribute this 1 over 26 into each of these two terms inside the brackets. When I do so, I get 5 over 26 minus 1 over 5 plus tangent x, and then I have a plus c. Well, 5 over 26 is a constant. Plus c right here is also a constant. Those two can be added to become a new constant. Therefore, this answer can be written as negative 1 over 5 plus tangent x plus k, where k is an arbitrary constant. Now you can see that this is exactly the same answer as the answer that we obtained for this integral using the trig substitution u equals tangent x. Alright, now if you would like to practice this method and evaluate an integral, I would like to give you a homework question. The homework question that I gave you last time for you to obtain the answer using the substitution u equals tangent x was integrate 1 over 4 cosine 2x plus 3 sine 2x plus 5 dx. Even for this question, you can see that 4, 3 and 5 form a Pythagorean triple, because 4 squared plus 3 squared is equal to 5 squared. So, if you would like to try the method discussed in the video, please try to answer this question using that method. I would like to give you a second question as well. So here's the second homework question. Integrate 1 over 20 cosine 3x minus 21 sine 3x plus 29. On the numerator, I have dx. Well, you need to pay attention on this negative symbol right here. That will have some impact. If you need a small hint, please note that cosine a plus b expansion is equal to cosine a times cosine b minus sine a times sine b. In addition to that, you must also pay attention to the given angle 3x. Well, if you need a hint for that section, all I have to say is, if you need to write cosine 3 theta, this can also be written using half angles as 2 cosine squared 3 theta over 2 minus 1. That is the same double angle identity used in a slightly different way. The official double angle identity that we need is cosine 2a is equal to 2 cosine squared a minus 1. Alright, now I think you have everything necessary to answer these questions. If you need any further help, please feel free to let me know. I hope you enjoyed this video. Thank you so much.